Let's next solve number 10. So what does it have? Let A be a ring and R be the nil radical of A. Okay, so that means R is the ideal consisting of all the nilpotent elements of A. Then we have to show that the following three statements are equivalent to one another. If any one of them is true, then the other two are also true. The first statement is that A has exactly one prime ideal. Alright. The second one says that every element of A is either a unit or nilpotent. And the third one states that the quotient ring of A by that nil radical R, this ring is a field. Although it's not given in the exercise, but I am sure that the author means a non-zero ring, because without that assumption the exercise just loses meaning. So I start like this. We need to assume that A is a non-zero ring. Alright. With that assumption, next we assume 1. 1 means that statement 1 which you do not see here, but that statement was this, that our ring A has exactly one prime ideal. Okay. Then by proposition 1.8, the nil radical R is prime. How? What is going on? You go back and see the statement of proposition 1.8, it tells us that the nil radical, which is the ideal of all nilpotent elements, is the intersection of all prime ideals in our ring, in any ring actually. But what is our assumption 1? That there is exactly one prime ideal. So if we take the intersection of that ideal, I mean there is just one. So the intersection will be that ideal itself, which however by proposition 1.8 has to be equal to R. That means R is equal to that unique prime ideal. That makes R itself a prime ideal. In general, in a ring, nil radical need not be a prime ideal, but in this specific case, it is. Okay. So we keep this fact here and then next concentrate on this other thing. Now you go back to theorem 1.3 and see what it says. It says that in any non-zero ring, there is at least one maximal ideal. There may be more than one, but at least one is there. Let's call that M. Okay, let's choose any such maximal ideal M, which however is prime because every maximal ideal is prime. But just now we concluded that the only prime ideal is R. Only prime ideal is coming from the assumption, but in this part we showed that it's equal to R. So M has to be equal to R. Okay. But then what can you say about this quotient ring A by R? It's just the quotient ring of A by the maximal ideal M. But you know from elementary ring theory, that such a quotient ring of a ring by a maximal ideal is a field. So that's how this becomes a field. So we now have statement 3 proved from statement 1. So we have this implication, 1 implies 3. So we continue the solution from here itself. Next, assume 3. That means we are now assuming that A/R, the quotient ring, is a field. And what is it that now we want to show? We now want to show that the second statement is also true. That means any element in the ring is either a unit or nilpotent. So you ideally should have taken any element A in capital A, but why are we taking it in this difference? Why are we not taking it inside R? Because if A belongs to R, then A is nilpotent, there is nothing to prove. So let A be not in R, which just means that A is not nilpotent. Now our aim is to show that A is then a unit in the ring capital A. Okay. Now A not being in R means what? What is the effect of this on the coset A plus R? A plus R will then not be equal to R. And what is R? R is the zero element of this quotient ring. That means A plus R then is a non-zero element in the quotient ring, which is a field by our hypothesis, this assumption. And that is why there will be a multiplicative inverse, some B plus R in A slash R, such that the product of A plus R and B plus R is the unit element, which actually in this book we are calling identity element with respect to multiplication, and that is 1 plus R, where in this ring, or AB plus R equals 1 plus R, because by the definition of multiplication in this ring, quotient ring, this product equals the coset AB plus R. And then by the condition for two cosets to be equal, you get this. AB minus 1 is an element in R. What does that mean? It means that AB minus 1 is a nilpotent element. But from exercise 1, you know that if you add the identity 1 to any nilpotent element, that means in particular this one say, then you get a unit. So that way AB becomes a unit in A. Now we are almost there. We actually want to show that A is a unit. But what does that mean? That AB is a unit in A. It means that there exists an element C in A such that AB times C is the identity. However, by associativity of multiplication, we then get this. A times BC is also equal to the identity. That means there is this element BC, which if you multiply with A, you get the identity. But then that just simply means that A is a unit in A. Now here finally we have it. So either A is a nilpotent element, that means it belongs to R, or if it lies outside R, then it has to be a unit. And that's how we have this implication. Statement 3 implies statement 2. Finally, let's assume 2. That means now we are assuming that in our ring, every element is either a unit or nilpotent. And we want to prove that 1 is a consequence. That means we now want to prove that there is exactly one prime ideal. Okay. So let P be any prime ideal of A. We are right now not saying anything about whether there is a prime ideal, although you may have already guessed that there is actually at least one prime ideal, but we are coming to that afterwards. Let us first see why P should be equal to the nil radical. Let P be any prime ideal of A. Because P is a proper ideal, P is not equal to A, so every element of P must be nilpotent. Why? Because by our hypothesis, which is statement 2, every element of P is either a unit or nilpotent. However, you know that if you have even one unit in an ideal, that is forced to be equal to the entire ring, which P is not. P is not the entire ring. So all the elements in P are forced to thus be nilpotent elements, which makes P what? That makes P a subset of R, because R is the set of all nilpotent elements. However, we already know that R is a subset of P. Why? Because by proposition 1.8, R is the intersection of all prime ideals. So it is a subset of all prime ideals in particular, and in particular R is a subset of P. So P is equal to R. That means if you find any ideal P in the ring which is a prime ideal, then that has to be equal to the nil radical. Note how I phrased this, if we find any prime ideal P. But shall we find any prime ideal P in A? Yes, that comes from theorem 1.3, which tells us that there is at least one maximal ideal which is prime. So there is at least one prime ideal. But then using this argument, we see that that has to be equal to R. So R is the unique prime ideal in our ring. which is what statement 1 says. So that's how 2 also implies 1. So the way we proved these things, 1 implies 3, 3 implies 2, and 2 implies 1. So it's forming a cycle. So that's why the 3 statements are equivalent to one another. If any one of them is true, then following this cycle you can reach the other 2.